Okay, this is the homework video for Module 6 acid-base reaction, titration basics. Okay, let's get into it. For multiple choice, question 1, a student prepares 0.1 mol per liter solution of sodium hydrogen carbonate using the following methods. Okay, so dried sodium hydrogen carbonate was dissolved in a beaker with deionized water. Solution was transferred into a volumetric flask with a funnel. The beaker and the funnel were rinsed and using deionized water, and the rinsing was discarded into the volumetric flask. The deionized water was added to the flask until the solution reached the mark as shown. Okay, there's pretty much nothing wrong with the steps. The only thing that's wrong is this step, right? The meniscus of the liquid isn't touching the mark. Okay, so it's actually below. The volume is below the requirement. Okay, meaning that the concentration at the end of the day will be higher. It's P. Students titrated sodium hydroxide solution with unknown concentration of oxalic acid. Standard solution. The following method was used in titration. Assuming each step was followed correctly, calculate the concentration for sodium hydroxide. So we rinse the pipette with a conical flask, right? So the conical flask with sodium hydroxide. This is bad. So the conical flask actually can only be rinsed with water. This is rinsing with sodium hydroxide, so that means we need to take in more volume to reach the endpoint. So we end up getting an inaccurate result because it would have a higher actual concentration because we actually use more volume than we need because we introduce more moles in the conical flask. Okay, so step 1 already tells you the answer. Question 3, it's rinsing technique. All right, so what burette or pipettes, you need to rinse it with whatever solution you placed in. So D is the right answer for it. Question 4, the table shows the endpoint and colors of some common pH indicators. Which pair indicator, when used in conjunction, is the most suitable for identifying the pH range of orange juice, which is 3? So we actually have 3. Either methyl orange would work or thermal blue would work. So A is the right answer. So make sure that you want to choose an indicator that changes color at the equivalence point, near the equivalence point, to produce a best estimate for the endpoint. Students pipetted 25 mils of sodium hydroxide into a conical flask, added a few drops of this. This is just basically neutralization reaction, so CV equals to CV. You can calculate the concentration very easily, okay? It's hydrochloric acid and sodium hydroxide, so it's 1:1 as well. Yeah, question 6, student does this, and I think this is, again, a very easy titration, but in this case, it would be sulfuric acid. So there's like a molar ratio, 2:1 to it. So you have to take C1V1 equals 2 times C2V2. Take care of the molar ratio, so you should be fine with this one. Question 3 as well. Question 3, you need to know that citric acid is a triprotic acid. And given the molar mass, but it's fine. It's just simple calculation, okay? So you calculate the concentration in moles per liter, and then you use the molar mass to convert it into grams per liter. Right? You should be able to do this. If not, let me know, and I'll go through in class. Question 8, equal volume of 4 0.1 mol per liter acids were titrated with the same sodium hydroxide solution. Which one requires the greatest volume? Changing color. Okay, so neutralization doesn't care about strength, right? It's always a completion reaction. So greatest volume. I think I picked this one wrong. What I meant was A, I think. So the idea is that we have equal concentration for all the acids, right? Citric acid is triprotic, so we require as 3 times as the amount of the base, right? Because it's triprotic. The ranking next will be sulfuric, okay? And so this question is actually, question 8 is actually A. Question 9, which statement best describes the equivalence point in a titration between strong acid and strong base? That's when you have equal molar of acid and base and just completely neutralizes, right? So C is the right choice. People would also choose B as the right choice, but this is not necessarily true. It's true when you have like 1-to-1 ratio, but it's not true if you don't have 1-to-1 ratio. Okay, but it's always true if you pick C, because when H plus and OH minus balances, that's completion. Question 10. For Ruby, sodium hydroxide was actually contaminated, and she was using it as a primary standard, which would cause the experiment to be invalid because the primary standard isn't a standard solution anymore. And because of that, contamination would yield a greater uh, mean tidal value, because you would actually need to put more volumes because sodium hydroxide has been contaminated. Question 11. Yeah, so rinsing technique for the first question, right? You want to rinse your pipette with deionized water and the solution that's in there, which is hydrochloric acid. Conical flask, rinse with deionized water only. And then burette, rinse with deionized water and sodium carbonate. Okay. And for question B, we just need to explain why A, B, C is wrong, and then what happens if I do this, right? So just carefully use a dot point to explain it. So A is incorrect as if the rinsing burette and the pipette with water would result in unaccounted dilution, right? We diluted the solution over titrating, so it's bad. It's altering the concentrations in a glassware, so it changes the number of moles. Whether it increases the tidal value or decreases the tidal value depends on how much did you use for the pipette or burette. Okay. Question B is selection B is incorrect as similar reasons, right? Because you're diluting the solutions with water. Question C is selection C is incorrect, where the conical flask must be rinsed with water only, but it's rinsing with solution, so increasing number of moles effectively increase the tidal value, right? So just carefully explain that. Moving on to question 12, we have 4.2 grams of sodium hydroxide dissolving in 500 mils of volumetric flask. What is the concentration of sodium hydroxide in solution? Well, you have the molar concentration, simply work it out, okay? C is equals to N over V, but we don't know N. N is equals to M over MM. Substitute your values. Question B, the sodium hydroxide solution is said to have a concentration of approximately 0.2 moles per liter. This is standardized by this much of HCl. So it becomes a secondary standard. The volume that's required to do this is this much. Simple titration, right? Work it out. Yeah, so be aware that you need to substitute values at the end. Oh, I forgot to give units. I guess I'm not in a clear mindset when I did this booklet, right? So unit is very important, right? I forget about it, which is really bad. Question 13. The concentration of acetic acid in a bottle of commercial soft drink was determined to be this much. So this is a question where you're given like a table, and then you have to ignore the first rough titration, right? Take the average of the series titrations, and then the rest is simply just what it is, right? Just be aware that you need to balance the equation. It's a molar ratio of 1 to 2, okay? You should be very familiar with how I do it, and then simplifying all the ratios just by doing math instead of doing like your mind thinking and stuff. It's very easy to make mistake. So check your answer. If you ever got any question, let me know. Question B. So student dissolve this much deionized water to explain why. Okay, so sodium hydroxide is not a good it's not a good ingredient for primary standard. I just sort of explained that because it will get contaminated and yield inaccurate result. So sodium hydroxide, remember the 4 points in the booklet? So I should talk about that. Right, so sodium hydroxide is not an appropriate choice of primary standard, considering sodium hydroxide is chemically unstable. It's hygroscopic, i.e. that it absorbs moisture from the air and will be contaminated quickly. Okay, also, sodium hydroxide has a smaller molar mass, causing a large percentage error when measuring mass. Question 14. Question 14 says a manufacturer of wine requires its product to have a malic acid concentration of this much weight by volume as a percentage. All right, so this unit here is a bit weird, and then I'll clarify a little. This weight by volume percentages means 8.0 grams per 100 mils of water. So you dissolve 8.0 gram of whatever thing into 100 ml water. and that's just what this is, right? That's just what it means. This percent means like in like 100% of where each portion is like 1 ml, so it's like per 100 ml, as in like a percentage. Yep, and everything else will be quite similar. Okay, so just write down your chemical reaction, and they tell you that malic acid is diprotic acid. You don't know the you don't know the chemical equation. They're giving you the molar mass, so you just write it as like a H2A or something to just express it. Okay, and then the rest of it is pretty straightforward. Just be aware that during the titration, the sample was like diluted, right? It was diluted 4 times, uh, and then we take only like 1/4 of it. It's like a little bit of um, a change in calculation that you need to sort of take into consideration. Okay, that's what I'm doing here. It's very good to like write a sentence to describe what is happening instead of just using numbers. Okay. So the answer is 7.2, which is satisfies the claim, which is very nice. Yes, it's like in order to compare with the weights and volume, you need to sort of convert that into the so-called grams per 100 ml, or you can convert this to moles per liter in the first place, and then use moles per liter to compare as well. That's fine. Question 15, we have a bunch of indicators, and I think this question is asking you to assess the usefulness of an indicator. Okay, so it's very nice if you can draw this little diagram. If you don't have a colored pen in a test, that's fine. You can sort of just shade your thing and then label it with like words, right? Yellow or orange is right on top of it. Okay, so assess the usefulness for using this type of indicator where it changes color at different solutions, right? You should know what these solutions represents. This is a strong acid, this is a strong base, this is a weak acid, this is a weak base, this is neutral, right? So it sort of tells you the pH changing range, color changing range of this indicator, and you should be able to plot this diagram. Okay, so for most of the neutral and base, right, this indicator is yellow, and it only changes color at some like sort of weak acid pH, and then changes color again when it's strong acid. So it is able to identify between strong acids, right? So if you have a strong acid and then you have a base, or you have a weak acid, you can see different colors. It is effective in determining strong and weak, right? So you have a strong, it will be here, you'll have red, and weak, you have orange or sometimes yellow, right? If you have a base, it will be yellow as well. However, it is ineffective if you have a strong base and a weak base, right? They will just be yellow anyway. You cannot distinguish away from that. Or you have strong base and neutral, or weak base and neutral. See, this is limitation. Make sure to write that down as well. Question B, is this indicator suitable for titrating a strong base and a weak acid? Titrating strong base and weak acid, we will end up with a basic salt. All right, so the equivalence point will end up with some pH over 7. All right, so we want to select an indicator that changes pH at a basic level, where this indicator does not change pH at basic level. It changes at acidic level, so it does not produce a good estimate for the endpoint. Okay, so sort of explain that. It's not suitable. In continuation, question 16 is a flowchart. All right, so and then it's like steps, right? Step A is like preparing standard solution. Step B is titration, and yada yada yada. I wrote a lot for this question, but the idea is to explain, as the question says, right? So explain each step carefully. Rinsing technique is a big thing, so I sort of write it in an introduction, right? So prior to all the steps of preparation, which is rinse everything, and volumetric flush rinse with only distilled water, burette is rinse with water, and then HCl is analyzed. As you can see how it's HCl being put into the burette, and then conical flush is rinsed with water only. Pipette is rinsed later. It's required. Pipette is rinsed with the standard solution, right? So this step here, we said it's rinsed later. We didn't say rinse with what because we don't have standard solution yet. We need to finish step A, and then we can say what is rinsed with pipette. Step A is the step requires the use of volumetric. Okay, that write this much, and then we weigh it out. Okay, the required amount of this is calculated, and you can even calculate that. Okay, so roughly this much is then added to a volumetric flush and then filled with deionized water to the meniscus, and sort of explain that, right? you also want to rinse the funnel that when you prepare the standard solution, just like some detail to ensure that everything is dissolved. Then we also rinse our 25 ml pipette. So we now have our standard solution, and we can rinse it now. Step B is just titration. And in this titration, you write down the equations as well, and say about the equivalence point, and then you want to choose like whatever indicator you want to choose. We will choosing method orange, indicates what color does it change from, and the pH range that it changes to. Okay. Right, 2 droplets of meth orange is added to the conical flask, and then we have sodium carbonate is there. So the initial color will be yellow, so it's indicating what color is changing. And then step C is just to conduct the titration and calculate the final titrations. Okay, this question is pretty involved. You need to answer a lot for each step because each step is very important. That's why this question is 8 marks. Okay, so in general, you want to go over the space that's provided. Okay, but definitely use low points, right? And this question is very suitable for low points. A difficulty for this question might be like people don't know because we have the freedom when we do titration to put whatever solution into the burette and the pipette, right? So in this question, it says 25 mils that's used, which means 25 mils is very exact. This is not like something you measure from a burette, right? This is like something you use a pipette for. So this is very clear about we are pipetting, right, the standard solution into the conical flask, but we are filling up the burette with our analyte. Okay, so this order must be ensured for you to be rinsing the glasswares properly. Okay, very difficult question. Question 17 is a secondary titration, and it involves I think it's secondary titration. It involves like a weak acid called KHP, commonly used. Okay, so question A is supposed to determine we're using the KHP to determine the sodium hydroxide solution, right? So we're standardizing the sodium hydroxide because it got contaminated, as given the context here. Okay, and then the question B is just to use the whatever concentration we got from the sodium hydroxide, the secondary standard, to titrate our real analyte, citric acid sample, and just be aware of the stoichiometric ratios. And I think this question should be pretty straightforward. Okay. Yeah, like you might got stuck on top of this, right? If you don't study organic chemistry, but this is like what it is. Okay, the chemical reaction should look like this. Right, that's it for this booklet. It's pretty shorter than physics, I think. We'll see you for the next booklet, and yep, enjoy chemistry.